Welcome back. This is 8.4 part 2. So this is the very last part of chapter 8. Because we have just now finished confidence intervals, we want to think about how do hypothesis tests and confidence intervals correspond to each other. So remember, both of these, a hypothesis test and a confidence interval, are procedures that we use to make an inference about a population parameter. So if we do these things correctly, they should give us the same result, meaning we should be able to make the same conclusion about the population parameter. So a couple of important things we want to think about when we're comparing a hypothesis test and a confidence interval. If we want to directly compare the results of a hypothesis test to a confidence interval, we want to make sure that our confidence interval and our hypothesis test have some certain corresponding specifications. That's what this first bullet is talking about. So we can only compare the results of a two-sided hypothesis test with a significance level of alpha to the results of a confidence interval with a particular confidence level. Now, I know that formula looks a little bit crazy, so I'm going to make some notes over here in the corner. So what this first bullet is saying, if we want to compare a hypothesis test with a confidence interval, first, the hypothesis test needs to be two-sided or two-tailed. And let's say the alpha level for the hypothesis test is 0.01. The confidence interval needs to have a confidence level of 99%. If the hypothesis test has an alpha level or a significance level of 0.05, the corresponding confidence interval needs to have a confidence level of 95%. Let's do one more. If the two-sided hypothesis test has a significance level of 0.10, then our confidence interval needs to have a confidence level of, if you guessed 90%, you are correct. So let's think about how are these related. So one is written as a proportion or a decimal. So all of these are written as a decimal. These are written as percentages out of 100. If you were to write them in the same format, meaning if you were to write these as percentages instead of proportions, then these would add to 100%. And that is how those are related. So that's the first thing we want to make sure we check when we are trying to compare a hypothesis test with a confidence interval. So a couple of other things that we want to think about. Remember, a hypothesis test has a null hypothesis and an alternative hypothesis. A confidence interval just has a low bound and an upper bound. So this second bullet, if the null value, meaning the value that's in our null hypothesis, is included in the interval, then that means it's a plausible value for the population parameter. If it's a plausible value for the population parameter, then we wouldn't reject that null hypothesis. Remember, our null hypothesis usually says something like, and I'm going to use a p for a proportion, p equals 0.7, right? So if I build a confidence interval, a corresponding confidence interval, and my confidence interval is 0.62 to 0.78. Well, 0.7 is in fact in my interval, which means 0.7 is a plausible value for our true population proportion. If this is a plausible value, then we wouldn't reject that null hypothesis. Thinking back to hypothesis tests, if we don't reject our null hypothesis, that means that our p-value that we would have gotten had we performed the entire hypothesis test should be greater than our significance level. So putting all of those pieces back together from hypothesis tests, but also relating them to a confidence interval. So now let's use this same example that I just made up, and let's make this, 0.67, okay? So now let's look at this second bullet, or this third bullet, excuse me. If the null value is not included in the interval, so let's check. 0.7 is not in our interval, which means 0.7 is not a plausible value for the population parameter. If it's not a plausible value, so if 0.7 is not in here and it's not a plausible value, then we're going to go ahead and reject that null hypothesis. If we did reject the null hypothesis, so think again back to hypothesis tests, if we came to the conclusion that we rejected the null hypothesis, that means that our p-value was smaller than alpha, had we actually calculated a p-value. So these bullets are going to help us make these conclusions without actually having to perform all of those detailed steps of computing a p-value, a test statistic, all of those things for a hypothesis test, nor do we need to actually carry out the steps it needed to build a confidence interval. So here we are really focused on comparing the results. And if we're given one, what could we say about a hypothesis test? If we're given the results of a hypothesis test, what could we say about a confidence interval? So I don't want you to think that now you have to do both from start to finish every single time. Here, this is more thinking about the relationship between the two and what can we say if we just know one of those things, what can we say about the other inference procedure. So here's our first example. This one here is giving us some computer output. So we'll talk about what this table here means as well as this table here in just a moment. But let's talk about the context first. I might be showing my age, but this is a game that was very popular when I was quite young. If you've never seen it before, there you go, showing my age. If you have seen it before, yay! So essentially here, there's some plastic cubes that you squish into this little blue fence area, and they are supposed to be ice cubes. You have these little guys standing on top, and you knock out one block at a time, kind of like Jenga, and whoever is the last person to make all of those fall loses. So that's the idea there. So we're talking here about the widths of these cubes. So this machine that produces the plastic cubes is designed to make cubes that are 29.5 millimeters wide, but of course the actual width varies a little bit. To ensure that the machine is working well, a supervisor inspects a random sample of 50 cubes every hour and measures their width. So in part A, we have the results of a hypothesis test with a significance level of 0.05. So let's take a look at these results to make sure we understand what this computer output is showing us. This is computer output directly from StatCrunch. So this is saying a one sample T summary hypothesis test. So one sample because we've just taken a sample of 50 cubes. T because this is a hypothesis test for a mean. So we would be doing a T test instead of a Z test for a proportion. Now let's take a look at our hypotheses. So our null hypothesis is that the true mean width of all of these plastic ice cubes really is 29.5 millimeters. Our alternative hypothesis, notice here, is two-sided, that the true mean width is not 29.5 millimeters. So we have all of this information. We've got our sample mean from our one sample of 50. We were given our standard error here. We have our degrees of freedom, which is our 50 minus 1. We have our t-test statistic, so again, we didn't have to calculate that. And then we're given our p-value. So a little bit of review, thinking back to what does this actually tell us and what decision would we make. So this p-value is in fact large because it's greater than our significance level. So because that p-value is greater than alpha, we fail to reject H naught, meaning we do not have convincing evidence that the true mean width of the cubes is different from 29.5 millimeters. So part B is giving us the results of a 95% confidence interval. So first of all, let's check to make sure that we can actually compare these. So here we have a two-sided hypothesis test with a 0.05 alpha level corresponding to a 95% confidence interval. So going back up to our bullet, two-sided hypothesis test, we've got that. We had 0.05 here, which means we should have 95% here. So we can compare these, and what we should see here is that the results of our confidence interval do help us make the same conclusion that we just made looking at the results of our hypothesis test. So remember we said we fail to reject H0. So we fail to reject this hypothesis. So that means we don't have convincing evidence that the true mean width of these cubes is different from 29.5 millimeters. So let's take a look at the results of our confidence interval. So again, a one sample t interval. Our output tells us we're doing a 95% confidence interval. We have our sample mean, we have our standard error, we have our degrees of freedom, and then we have our lower limit and our upper limit. So the only thing different between these two tables here is that we've got hypotheses in the first one, and then we have a t-stat and a p-value, whereas here we have a lower limit and an upper limit. That's our low bound and our high bound for our interval. So let's check. Is 29.55 in this interval? So it is in this, 29.5. 29.5 is in this interval. It's a little bit lower than this guy here. So because 29.5 is included in our interval, that means that 29.5 millimeters is a plausible value for this true mean width of these plastic ice cubes. So if it is a plausible value, so 29.5 is a plausible value, that means we would not reject that mu equals 29.5. So what I want you to see is that we got the same conclusion based on the fact that 29.5 millimeters is included in our interval, and because our p-value was bigger than alpha here. So we've got the results of a hypothesis test, the results of a confidence interval. We know that this hypothesis test with this significance level here, it's two-sided, does in fact correspond to this confidence interval. So we know that we should get the same results for both of those things. Flipping on to our second and last example, here we are talking about the average number of crocodiles across sanctuaries and wetlands in Indonesia. So historical data suggests that the true number of crocodiles in those areas is 300. Zoologists think the average has changed. So thinking back to hypothesis test language, if we think the average has changed, that's going to be a two-sided test. They took a random sample of 60 different crocodile habitats and constructed a 96% confidence interval for the average number of crocodiles per habitat to be 285 to 298. So this first example is, or this first part, part A is just kind of a review of the different pieces of our confidence interval. So what does the sample mean and what is the margin of error? So sample mean, what is the number that we added and subtracted the margin of error to? Well, remember that sample mean or that point estimate is always directly in the middle of those two things, those two bounds. So we can simply find the average there by adding and dividing by 2. So our x bar is going to be 29.5. Remember our formula is x bar plus or minus t star times s over square root of n. So we just found x bar because we knew our upper bound, we knew our lower bound, and we know that when we take our x bar and subtract our margin of error, we get our low bound. When we take our x bar and add our margin of error, we get our upper bound. So our x bar has to be directly in between these two things. That's why we averaged those bounds together to find the middle. Remember, this last part here is our margin of error. So now that we have our x bar, our sample mean, we just need to know how much did we add to get our upper bound, how much did we subtract to get our lower bound. So we're just looking for the distance between our x bar and our upper bound, or x bar and our lower bound. So if we do our 298, which is our upper bound, minus our x bar, we would get 6.5. You could do your x bar minus your low bound, you would also get 6.5. So we talked a little bit about part B already. What are the null and alternative hypotheses for the corresponding significance test? So if we're trying to write the hypotheses for a hypothesis test that corresponds to a 96% confidence interval, we want to first make sure that it's a two-sided test. So there's our two-sidedness. Part C, what do we know about our p-value? So first of all, we know that our alpha has to correspond to this confidence level, so our alpha has to be 0.04. Now let's check is our null value included in our interval? So looking at our interval, 300 is not included in our interval here, which means 300 is not a plausible value for our true mean. If 300 is not a plausible value, we would be rejecting our null hypothesis. Again, going back to hypothesis test, we would only reject our null hypothesis if we had a small p-value. Small for this case would have to mean that our p-value is smaller than our alpha level. So I do want you to think about all of these different pieces here. I know oftentimes students just try to read this question and skip right to here, but I think it's really important to think about, well, first, what is my alpha level? Let's compare my null value to my confidence interval. Let me make a decision about the null hypothesis. Then, based on that decision, does that mean our p-value is big? Does that mean our p-value is small? How big? How small? Then you can make this statement here. So notice here, we're not actually calculating the p-value. We're just saying that it's quote unquote small, meaning it's smaller than our significance level because we know we would have rejected our null hypothesis. All right, this last part here, we want to think about what if we changed our hypotheses. So if the zoologist thought the average had increased, not just changed, but increased, how do our hypotheses change? So here, notice we've changed our hypothesis to greater than because the zoologists now think the average has increased. So we want to think about how does that change our conclusion for different hypothesis tests. So let's go back for a second and think about this conclusion. So our conclusion before for the two-sided test, we knew our p-value was smaller than 0.04. That was for a two-sided test. Recall in our two-sided test, we were looking at the area of both tails, right? So if we know that the area of both tails is less than 0.04 added together, once we make this into a one-sided test, that means that this area here has to be less than half of that amount because this is now a one-sided test. These two tails together have to be less than 0.04, so one of these tails has to be less than 0.02, half of that 0.04. So that's how we're getting this first one here. So now let's think about what if alpha was 0.04? Well, if alpha was 0.04, we would still reject H naught because our p-value that we know is less than 0.02 is also less than 0.04. That p-value that's smaller than 0.02 is also less than 0.06, also less than 0.02. So we would reject our null hypothesis in all three of these cases. So again, if we flip over, we've got, if you've already done this one here, this one was solving for sample size. You could have done that one after 8.4 part 1. If you haven't done it, maybe try that one now. And then this one here corresponds to 8.4 part 2, looking at the correspondence between hypothesis tests and confidence intervals.